Hello, I am Dr. Jorge Nunez. I'm a planetary scientist and astrobiologist. I'm also supervisor of the Moon to Mars Exploration section at the Johns Hopkins Applied Physics Laboratory. So let's talk about dust and regolith. We mentioned dust and its electrostatics, but we haven't really defined dust. So let's go ahead and describe dust and regolith materials in detail. Dust and regolith form part of the topmost layers of the upper lunar crust, as shown in the schematic on the left. The regolith layer comprises approximately the first 4 to 10 meters of the lunar crust, and the lunar dust commonly refers to the finest fraction of the lunar regolith layer. Lunar dust generally refers to the very finest size fraction, with grains typically less than 50 micrometers in size, although others have defined it as less than 10 to 20 micrometers in size. Dust particles are fine, loose, and sharp, which results in their stubborn adhesion to surfaces. In addition, they can easily be respirated without any protection, thereby posing a hazard to human health. In contrast, regolith is an unconsolidated debris that can be comprised of crystalline rocks, breccias, and large clasts. Dust and regolith are both generated by mechanical weathering caused by impact events large and small on the moon. As such, they share many characteristics, including grain sharpness and complex geometry. Depending on the location on the moon, these materials have variable mineral compositions, and since they are minerals, they are electrically and thermally insulating. So let's address specific challenges associated with each. Because of the fine-grained character of lunar dust, it presents separate challenges from the regolith. In particular, dust can be readily lofted and transported due to natural or human-generated events on the lunar surface, such as impact events, landings, and vehicle movement or walking. There is also evidence that dust can be transported due to the lunar plasma environment, and electrostatic forces contribute to the prevalence of the dust cloud close to the lunar surface. The interplay of electrostatic charging and cohesion forces leads to the stubborn adhesion of lunar dust to surfaces that can cause all sorts of issues, as listed in the table on the right. Dust contaminants can significantly affect passive thermal management systems, like radiators, and block and disturb measurements from optical systems. Being glassy and abrasive, lunar dust is also responsible for abrasion damage to all sorts of materials surfaces, particularly to soft textiles. Lunar dust is also the portion of the lunar regolith that causes problems for seals, joints, and similar internal surfaces, affecting their function and lifetime. Of note is the challenge to human health, as dust grains are the smallest respirable particles of the lunar surface, which can adhere to lung tissue and can also cause eye and skin irritation. Okay, so let's continue talking about some of the challenges posed by lunar dust. Here are a few examples of documented astronaut experiences with lunar dust. Lunar dust was pervasive, accumulating on astronaut suits, particularly at the zippers and seals that posed a risk to their sealing capability. It was also very challenging to keep dust away from the vehicle cabin and lunar modules, demanding future active mechanisms or barriers that can remove dust, such as airlocks. Apollo astronauts also had the uncomfortable experience of breathing the lunar dust inside the lunar module, which they described as smelling like wet ashes or gunpowder, and caused them to have allergy symptoms such as runny noses and watery eyes. Okay, so let's talk about some of the design considerations. The best way to engineer for this environment is to consider technologies that mitigate and or tolerate the effects of lunar dust. This can include incorporating passive or active technologies. Some suggestions include the use of dust monitors, material coatings, brushes, and electrodynamic dust shields, such as the one shown on the right. To identify the most suitable technology for your system, it is best to do high-fidelity tests that include one or more suitable lunar simulants and use a test method that targets your need. Ensure that you have identified a test facility, preferably one that may enable you to approximate the relevant environment. Reminder to refer to the LSIC Facilities Directory for dirty systems that can facilitate your testing needs, such as the Advanced Planetary Excavator at NASA Glenn Research Center, used to expose seal rotary joints to environmental dust. Another example of a dust mitigation technology is a dust-tolerant coating, where dust loading and abrasion tests prove critical for qualification. Overall, your system should be evaluated for specific dust-induced effects and their consequent risks to hardware, system function, and durability. This can be very difficult, and NASA has recognized that preparing and testing systems for this environment can be very tricky. To this need, NASA has generated different standards and guides to assist with dust challenges, such as the NASA Standard 1008 classifications and requirements for testing systems and hardware to be exposed to dust in planetary environments. Another helpful document is the Lunar Dust Mitigation Guide and reference. These references and associated documents can be found in the Lunar Engineering 101 website. Thank you for watching this module. I hope this provides you with a better understanding of the lunar dust and the challenges that it may pose to your system.
Hello, I am Dr. Karen Stockstill-Cahill. I'm a planetary geologist at the Johns Hopkins Applied Physics Laboratory, and I'm the Deputy Director of the Lunar Surface Innovation Consortium, or LSIC. I'm going to talk about lunar regolith characteristics. Regolith characteristics are very interesting. The composition depends on the location on the moon. For example, highlands are dominated by plagioclase feldspar, an aluminosilicate mineral that contains sodium and calcium, which we are very familiar with since they are also fundamental constituents of our Earth's crust. Mare regions are dominated by mafic minerals, which are darker in color and richer in magnesium and iron. But regardless of where you are and the corresponding composition, all regolith is fragmented due to the constant bombardment of meteoroids on the lunar surface, as well as previous volcanic activity on the moon. The regolith is also characterized by the presence of glassy, sharp, and fragile agglutinates, as those shown in the images on the right for Apollo samples. Agglutinates can be very porous, ranging from 40 to 45% porosity on average. Of absolute importance is to be aware of the unique geotechnical properties of regolith. Regolith has variable strength and deformation characteristics, which are intimately related to its compressibility, cohesion, and trafficability, or ability to support traction. Now let's talk about volatiles. Volatiles are mobile chemical elements or molecular compounds that are often components of the lunar regolith. Their existence on the moon has been a topic of interest to scientists and engineers for many years, since volatiles can inform us on the formation history of the moon, the Earth, and the solar system, as well as serve as resources to support human presence and lunar exploration. Suspected to be generated from comet impacts, asteroid collisions, and solar wind particles, as well as being endogenous to the moon, these species travel along the lunar surface and through its exosphere until they are either lost to sublimation or ionizing vents, adsorbed on or trapped in lunar grains, or buried deep within regolith layers as deposits. The dynamics of volatile molecular residence time, schematically shown on the right, are determined by the regolith chemistry and surface temperature. The most abundant volatiles on the moon are water and hydroxyl. Other volatiles include carbon dioxide, ammonia, argon, and helium, among others, but these species are present only in trace amounts. The presence of water is suspected to be variable across the moon, but most notably in permanently shattered regions near the lunar poles, where long-term condensation is possible thanks to the lack of sunlight and sustained cryogenic temperatures. For example, the South Pole is suspected to contain deposits of water ice that may be used for drinking, cooling, producing oxygen, and making fuel. Indeed, the L-Cross impact experiment, which impacted into Cabeus crater in a hydrogen-rich area near the South Pole, revealed about 5% porous water ice in the regolith. This was the first in-situ proof of water ice on the moon. In addition, on the illuminated moon, pyroclastic deposits of orange glass beads were found to be enriched with volatile species like hydroxyl, zinc, lead, sulfur, chlorine, and they had a thin coating of condensed volatiles. These properties present a few challenges. Unconsolidated regolith layers can be easily moved around and may land on critical surfaces. Recall that the regolith also includes a dust component, so any disturbance of the regolith material will also include the problems associated with dust lofting and contamination. Additionally, the regolith layer is not one solid slab of material with the exact same properties across its entire thickness. There are lower confining stresses at the very top, which vary as you change depth, along with associated changes in the relative density. Regolith is also very abrasive and can cut through soft textiles as well as abrade mechanisms. The insulating character of the regolith makes it subject to plasma-generated transport and arcing, which can affect electronics or ungrounded hardware in direct contact. And it's important to note that there are numerous challenges associated with the development of lunar regolith simulants, as well as how to test with them. There are challenges to using Earth-based materials because they are inherently different than what is on the Moon. The overall mineral composition can be difficult to replicate. For example, terrestrial plagioclase feldspar tends to contain a lot more sodium in contrast to lunar materials. Additionally, Earth-based soils are generally not as iron-rich and lack nanophase iron, which is unique to the lunar soil and is a result of exposure to the space environment. While techniques exist to approximate space weathering of simulants, they are not currently applicable to large volumes of material. Now let's talk about design considerations. Systems for the lunar surface will either be completely isolated from the lunar regolith, be in minimal contact with the regolith, actively interact with the regolith, or make use of regolith materials for an in situ resource utilization purpose. In any of those categories, you should evaluate the needs of your design based on the regolith properties that will affect it the most. A mobile asset will need to test its components for traction and durability against constant loaded contact with the regolith. Meanwhile, a lunar habitat or static system should account for the load-bearing ability of the regolith layers in its structural design and thermal implications. Manufacturing using regolith is an active area of research where properties like viscosity play a huge role, not to mention how the reduced gravity complicates the process. Furthermore, the choice of simulants matter. It is important to consider how differences in composition, particle size distributions, particle shape, and angularity differ from those in lunar regolith, and how those differences can affect your tests. There are several resources available, including the NASA Lunar Regolith Simulant User's Guide and the LSIC Lunar Simulant Assessment Reports. Finally, plan accordingly for the acquisition of your simulant. Simulant providers may need a big lead time to produce it. Thank you for watching this module on dust and regolith.